those of you that have already got to the point of exporting the process, you can come here and see this R button, R blue button there. You can just click on that to take you to the main folder of the project inside our studio. And then you can click on Markdown and open the session 2 partial. And we want to see that appearing up here, that script. And I'm also going to open the complete for myself, which you don't have yet. But just so I can also have my cheat sheet here to make sure I'm not forgetting anything. Perfect. All right, so I guess as far as I can tell, I think we're ready to continue here. And if I don't hear otherwise, I'm gonna start going with the session 2. Okay, I'm gonna get started then. So if you already have the partial 2 open on your screen, I wanna, well, you know what? First, let's do this. Let's just come on the side here and let's just click on that broom and clean everything that we have there and have like an empty environment to start with. So if you can just do that first, is just by clicking on that broom icon there. And so we're already we are all good to get started with session 2. So I just want to invite you again to just load all the packages on that first chunk by clicking on the play button. We're going to be using them. And as I was telling you earlier, the first thing that we're going to do here is import the processed version of our Wrangle dataset. So we just come here, and now because it is a CSV, we're going to use the read_CSV function. Just open and close quotation marks, have your cursor blinking in between them. We need to get outside first of the markdown folder. We do that by typing .. and hit tab. You browse into the data folder, hit tab again, and you should have 2 options now. We want to select the process.csv option. So if we just run that and just print it just to check, make sure that we got everything we needed. We should have 16 rows and 4 columns, and the columns should be potassium rate, kilograms per hectare, RAP location, and potassium percentage. So this is what we should have at this point. Okay, so very quickly here, I just want to do one plot just for us to explore this data set and see what's going on in a plot format. So let's start with calling Ggplot. The first thing we say here is the data set name, so soyk_w. Add a comma. We add the AES function to inform the aesthetics of this plot. So on the X, I want to have, I'm just going to come up here just to copy and paste. I want to have the potassium rate, kilograms per hectare on the X. And on the Y, I want to have the K_PCT. I want to go to the end of that Ggplot call, add a plus, hit enter, and ask for geom_point. And again, call the AES function and say color equals location. Let me bring this a little bit higher on my screen. Awesome. If we just run this just to see if it's doing what we were hoping. It's taking a little while. Okay, there you go. So we do see that the colors are representing different locations, and we have, kind of looks like we have 2 different groups, right? So locations A1 and S1 on the top, and the O2 and W1 on the bottom. And now, just to explore this a little bit further, I also wanted to add a trend line. So for that, we add a plus, hit enter, and do geom_smooth. And I want to change, if we just run this, it's going to be a spline, meaning that it's going to be a wiggly line. I want to actually change that and have a linear model type. So for that, we do method equals ln for linear model, and just run this. Taking a little moment here to run. Interesting. Oh, actually, it did not work. And that's because, why was that? Well, I think I had to actually had this color up here. So sorry, on the Ggplot call, we can just go back and say color equals location. So that will apply that to all the layers coming after it. And that should fix the, or should have a trend line for each one of the locations individually. All right, there we go. So if we look at it, it looks like for the locations on the bottom here, it looks like as you increase potassium rate, you're increasing potassium percentage on the leaf as well. And for the ones on the top, I don't know, it kind of looks like perhaps almost not increasing potassium concentration with potassium rate, or even decreasing for some reason. But this just gives us an indication that there are different types of responses across these locations, right? Okay, so that's basically all I wanted to do here. I'm just gonna leave this up for just another second so you guys can catch up. And let's just move on. Okay, so I already left this part of the code for you, which is basically just transforming wrap and location into a factor. This is really important for the wrap effect, because if we don't do this and we include wrap as a numerical in the model is going to try to calculate an intercept and a slope over blocks, which is not what we want. Because blocks 1, 2, 3, and 4 are just the names of the blocks, but it does not mean that block 2 is anything more than block 1, or that block 4 is more than block 2 or 3. They could have just been named A, B, C, D and have the same meaning as far as we're concerned. And so just to force R to see them as characters or as a factor rather than a number, I'm just transforming or creating this column here, F wrap. I just add the F in front of it just to tell me that it's being treated as factor, and F location as well. So if we just run that, it is basically, now we have these two extra columns, F wrap and F location, and they're both factors. So that's what we wanted to get into to modeling just one of the locations. So the next step here, so here's the mindset I want to explain to you, and maybe you came across this. So we have this data set where we measure potassium in 4 locations, right? And let's say I wanted to run an Anova or maybe a regression in only one of the locations, but my data set has all 4, right? Intuitively, what I would do here if I just want to run in one location is to filter, right? So here in this next chunk, we're basically just filtering the first location, which is S1. So starting with the data set above and location and filtering wherever location is equal to S1. If you just run that and print it, you're going to see that we have only 16 rows. And before we had like 64, right? So 64 with all the locations. Now we have 16 only where location is equal to S1. So this is what I would do, at least in the past, if I just wanted to run for one location, right? Okay, so let's run our regression then for this one single location called S1. So this first part of the code here, I'm not going to get too much into that, but it's just how our calculate, or any software really calculates, applies restrictions to the matrix to calculate model parameters. That's all you need to know, I guess, for now, and don't need to worry much about that. So let's just come here on the next row, add the assign symbol, and let's use the function lm. So just a fixed effect model. And let me just, so the name of, sorry, I'm just gonna go up here. The name of our data set, again, is soyk w2 underscore s1, because it only has one location. And I just brought that here just so we can copy and paste the column names into the model description. So our response variable is k percentage, right? So k PCT. Then we use the tilde. And now on the right side of this tilde here, because it is a randomized complete block design, we have to specify the block effect. And the block effect is on this frep column. So we say frep plus, and now our treatment structure, which is basically just potassium rate in kilograms per hectare. And notice here how potassium rate is numerical, is double. And that is on purpose, because I want to run a regression. If I wanted to run an ANOVA, potassium rate would have to be a factor as well. But we're not doing that, so this is what we end up with. And then I add a comma, hit enter, and then we just say data equals this data set. So wherever that is coming from. Now, don't only run this part. Make sure you also run that first options there, and then run the model function. So if you were successful running it, we got the model. Now let's use this function called tidy to look into the coefficients of this model and also the p-values. So if you just run that, we see that we have an intercept and then frep 1, 2, 3, and a potassium rate. So really, this is the overall intercept, and this is the slope that we have for the response. So for this location S1, the slope is negative. Look at that. So if we go, you don't have to go back. I just want to go back to show you. If we go back up here, we see that location S1 is the blue one, and it does seem to be a negative slope there. So that's what the coefficient is telling us. And if we just, so I went back to that tidy chunk. If we just go on the right here, we see that the p-value, or the significance of those p-values, and the significance of the slope is 4.7 to the -1, meaning that this is 0.47, meaning that it would not be significant, right? It's highly non-significant if you think of an alpha of 0.05. Okay, another way of looking at this is also to use the Anova function. So if you come here, we say Anova, and then we just copy and paste that name right there, the soyk reg s1, which is our regression model. And we say type equals 3 because it's the type 3 sum of the squares. We have a very similar, or not a very similar, but another way of looking at this where the rep effect was highly non-significant and the potassium rate effect, or the slope of that regression, was also highly non-significant. Okay, so let's, as I normally like to bring this point of checking residuals and checking model assumptions through residuals, I want to do that here as well. So to do that, first we need to extract the residuals from this model before we can look into them. So let's use, coming on this next chunk here, let's use the function augment from package broom, and then we just say here the name of the model. So not the data set, but the actual model. That is the soyk reg s1. If we just run this and we print this object that is the augmented data set, we see that the function augment basically takes our data set that we use for the model with the same columns going into the model, which were kPCT, frep, and potassium rate. And then now it adds extra columns here that are related to the residuals of this model. So the dot fitted, resid.hat, and all those standardized residuals, Cook's distance. So those are all things that we can use to check for model assumptions. So the first one that I want to do here is check the standardized residual versus the fitted values. And this is really important. I mean, I don't know, like, this is a really important point of just always checking the assumptions of our models, which are normally based on the residuals and not necessarily on the raw data itself. So let's just use a Ggplot call here. I just pasted here that augmented object that we created above. And then I'm gonna call the AES function. On the X, I wanna have dot fitted. On the Y, I wanna have the dot std dot resed, so standardized residual. Add a plus, hit enter. And then I wanna look into, like, I wanna have a scatter plot here. So that's we use the geom point for that. And if we just run that, just to see what we got. So this is what we have as of now. However, one of the assumptions that we want to check is that the residuals are homogeneously distributed around 0, and that we don't have any standardized residual above 3 or below -3. So to have those visual lines for us to make it easier to really see if our assumptions are being met, let's just add here a geom_age line, which is for horizontal line, where it has an argument called y-intercept. So we say y-intercept, and I want to give it 3 numbers. So we use the concatenate function, the C function, and I say -3, 0, and 3. And I just run that. So now we have those 3 lines for us to base our judgment. And it does seem like the points are scattered around the 0 line, but I really would like to see if there is any strong pattern behind these points. To do that, we can also come back to the code, add a plus, hit enter, and then add the geom smooth function, and just leave it as a spline function and run it, because that's going to really add a trend line there with an error bar. So what we're looking for here is to really make sure that the standard error is overlapping the 0 on the y-axis throughout all the values of the x-axis, like it is here. I mean, it's not in that very brief part right there, but I wouldn't really worry much about it. So if this is true, like you're not seeing a strong pattern on this wiggly line, and all the standard errors are really overlapping the 0 line, and you don't have any points above 3 or below -3, then your model assumptions are most likely met. This is how I would check for model assumptions anyways. And then if we go one step further here, so here we just checked for, so what we checked here was the presence of outliers, so above 3 or below -3, and also the homogeneity of the variance of our points, which also has been checked by using the standard error of the wiggly line here, of the smooth line. Now we have this plot does not really help us to check the normality assumption of our residuals. And that's what we're going to check next. So if you come on the next chunk here, let's call Ggplot again. And the data that we're going to give is the same as we did above. So the augmented data set. And then on the AES function, we're going to say simple equals .std.resid. So it's kind of a new aesthetics that we don't really use that often. That's called simple. Oops. And then you add a plus at the end of this Ggplot call, hit enter, and we're going to add this stat_QQ function. Add a plus, hit enter, and stat_QQ_line. So this is going to add a quantile plot in line that help us to see if our residuals follow the expected normal distribution that you would like to see. And we check that by basically seeing if the points are falling on that black line. So that black line would be the expected normal distribution if the residuals were normal, and then we actually plot the residuals as points to see how far they are from that line. Here we see that maybe they're like some residuals that are not really on top of that line, but they're not terrible looking either. So I would say our model assumptions have been met. Let's just keep going. Okay, so here's where the automation or the iteration part comes in. This is going to be maybe a little bit complex, so I just want to ask you for a full attention here. So, okay, I stopped right here, right? And this was, I just checked the assumptions for the model of one location. And let's say after this point, I would extract means, pairwise comparisons, and make a plot for this one location. However, let's say I want to do this, the same process for each one of the locations. So in this case, we have 4. But let's say in your case, maybe you have 20, or maybe you have even more than that. Before I learn how to do what I'm going to show you now, I would basically just go back all the way up to my code, change the location here. So instead of, okay, I did this all for F1. Sorry, I'm going crazy up and down here. Let me see where I filtered. No, it was lower here. Yeah, I'll basically come back here, change my location to a different one, and just rerun the entire script again, and then export the plots and graphs. And that's, and you know, for this data set here with 4 locations, that is not too bad of a process, right? It's not like you're only doing this 4 times anyways. But imagine that you actually have multiple locations, right? 20 or 40 or even more. Then that strategy of just going back to a new location and redoing everything gets old very quickly, right? So I just want to show you here how we can actually automate this process and let R do for us this process of basically going and changing the location and applying everything, but let R do that for us instead of you going manually doing all this. So if you just come here on this next chunk, we're going to call this soyk reg all. I want to put the assign symbol there, and then the first data set that we're going to use is soyk underscore w2, which is the same data set that before we filtered by location, right? So soyk underscore w2, it has all 4 locations. As you can see, 64 rows, all 4 locations. So now the way that this works is let's add a pipe, hit enter. Let's use the function group by and say group by F location, which is a column in our data set. So we're grouping by F location, add another pipe, hit enter, and we're going to use the function nest. This is one of the key differences here for doing automation. If we just stop here and run this and print this result here, the soyk reg all, look what happened. This is something that if you're seeing this for the first time, it's kind of weird, like if this is the first time you're seeing it, because what happened is we have 1 row for each location and we have that F location column, but now everything else has been compressed by location into a table or a data frame, and it's part of 1 cell only. So this first value of the data column here is all the data rows combined in 1 cell that were part of, that had an F location equals to A1. And to preview that, it's kind of difficult to see this way. But what I want to do is just call the name of this object that we just created, use the $sign to get into that data column, and I'm going to use the brackets to sample that the first cell. Okay, so if we just run this data set here, all these columns, like 5 columns and 16 rows, are actually squeezed and are 1 cell in this data set here. That's kind of crazy, right? That you have data sets inside data set, inside one data set. So it's a little bit crazy of a concept, but it's really what allows us to do iteration here. Okay, so now that I showed you this crazy concept of nesting data sets, so data sets inside data sets, let's use this and fit the same model as we had before. So we add the pipe there, hit enter. We're going to use a mutate function. So remember that a mutate function is going to create a new column, right? So we want to create a new column right here next to data. That's going to be our model. So let's call this mod equals. So if we just come here, so if we just start typing like lm this tilde that, it's not going to work because it is a nested data set. For us to make use of this nested structure, we have to use a function that's called map. So you can just say map, open and close parentheses like that. So this map function is what actually interprets this nested structure into the data set. So the first thing that we say to this function is the name of the column that has whatever you want to iterate over. In our case, is the data. But this data column, the name of the column is data, right? So we say data because that's where the nested data frames by location are. So we say data, add a comma, hit enter. Let me just do this so we can see. And the way that you specify this is using now a tilde. And now you just type the function as you would normally. So we say ln tilde ln, and then we're going to say k underscore pct tilde frep, that's the block effect, plus k underscore rate underscore kgha. So that's our formula. And now we have to still give that, so add a comma, hit enter. We still have to tell it what is the data argument of the lm function. So we say data equals. However, here's a very important trick. You cannot say data equals data because, I mean, I'm sorry that it's kind of confusing here, but the column name that has the data sets, it is called data that we specify right there. But here, inside this map function, now that we set on the first argument the name of the column that we want to map over, now inside this function, we do not call that by that name. We actually call it by .x. So .x is kind of like a placeholder inside the lm function that will return back to that name that you specified as the first argument. I know it's a little bit confusing, maybe a lot confusing, but it is just, I guess, it is the way it is. So let's just run this and see what happens, right? So we ran it. Let's just print the soy k reg all and see what's going on inside of it. So now we have this column called mod because that's the name that we gave in the mutate. And now notice that the type of the objects inside this column mod is not a Tibbo anymore. It's a NAS3 type object of the type LM. And that makes sense, right? Because that is the object type of LM objects. That's kind of what it is. But it's kind of crazy that now you have a column that has data sets inside of it instead of just a value. And you have another column that has model object fits instead of a value. It's mind-blowing, I guess, if you're seeing it for the first time. But that's kind of how the map works with the nest as well. So let's just try to access this first model fit here. So we just use the $, say mod, and then let's just use the bracket notation to extract that first cell right there. If we print it, it is a model fit object coming from that first location. Kind of crazy, right? But that's what it is. So now that we see that, we kind of understand what the nesting does, right? So the nesting basically creates subsets of your data set based on a group by variable that in our case is f location, and then it starts building on these nested column or nested data sets to create new columns that you specify by using the map function. So, we're kind of running a little bit out of time. So in my original script that I will be sending you guys after this, I had actually calculated the residuals doing the augment, and also did the plot, the Ggplot, looking at the standardized residual by fitted for each one of the locations. I'm gonna skip those 2 steps here just for the interest of time, because those are important and you will have them afterwards. But I just want to show you something else that may be more interesting for the time being, which is, okay, so now we have this model, right? We have the model fits by location. But what if I actually wanted to extract the coefficients from each one of these models for each one of the locations, like get the intercept and the slope for each one of the locations to make a plot afterwards? So we can just add a pipe here, hit tab. Let's use the mutate function again, and let's call this tidy. I just want to give the name of the column as tidy. And as we know, we have to use the map function to use this nested structure. And the tidy, we're going to end up using the tidy function here, which means that we need to give it a model fit object, which is that mod column that we had. So that's the column we had. I just want to hit enter here to make it easier to see. And then again, we have to start with the 2-day notation here. And the function name is tidy as well. So tidy, and remember that inside map, we use .x. We did not say mod. We say mod just as the first argument, but then inside, like after the 2-day, you call that first argument by the name .x. That's the placeholder, right? So if we just run this, I just want to show you what happens, and we're going to build up afterwards. So if we just call that, and I'm going to get into that tidy column. Well, let me just print this so we can see. So now we have a tidy column that is again a tibble, but that was created based on the mod column, right? That's what we did right there. But what is inside the tidy? Let's just open up the first cell of that tidy column there. Is this. And what my goal here is to only have the intercept and the slope of these. And I want them to be as columns and not like, I want the intercept to be a column and the K rate to be another column, and to have the estimate values underneath them instead of how they are here. So we're going to do a little bit of wrangling. If you want to come back here where we had the tidy, we're going to add a pipe there. First thing I want to do is use a select function, which I always call the dplyr package first. And we talked about this already. And I just want to keep the term and the estimate columns. So term underscore estimate. Okay. If I just run this and print again that first data set, this is what we have. Okay. So we come back here to the select, add another pipe, hit enter, and now I want to use the pivot underscore wider function. So the pivot wider does kind of the opposite of what the pivot longer did. So now what I want to do is take each one of these values under term and have them being the column names of the new columns and have the estimate values underneath them, right? So to do that, this pivot wider function has an argument called names from. So you say, what is the column, the current column name where the names of the future columns are stored in, which is term. So we just say names from term, add a comma, hit enter, and then it has another argument that is values from, which is basically the current estimate column name. And if we just run this and print this result so you can see what happened, this is what happened. So I'm doing this because I'm really interested in this intercept and this potassium rate that is the actual slope of the regression. However, I'm not a huge fan of using parentheses in column names. So I want to come back here after the pivot wider, add a pipe, hit enter, and just rename that. So I'm going to use the function called rename, and I'm going to say intercept equals this here. And you're going to notice something now. If I just copy that and I paste here, are actually things that those parentheses that are part of the name are things, those are actual parentheses in functions and not as part of the name. To make R understand that they're also part of the name, we have to add this apostrophe before and after. And you can notice that after I close the second apostrophe, the color of this parenthesis changes. Right now it's kind of like a light blue, and if I close it, it becomes white. So now R knows that this is an actual column name and not parentheses in the function. And if you're looking for, on your keyboard, there's like quotation marks, which are the two symbols. And then there is another way of doing quotation marks with just one bracket or one thing. And this here that I'm using is neither of those. It's actually apostrophe, which on my keyboard is on top of the tab button or the tab key. So all the way to the left, almost on the top of my keyboard. That's where I find this symbol here. If this intercept becomes green, or in my case it would be green because it would be quotation marks, that is the wrong symbol you're using. It needs to not turn green. It needs to turn, in my case, white. Okay, so if I just run this and then run again, we see now that we have intercept in a more readable name, and then the slope, which is the K rate kilograms per hectare. And I want to show you another trick here before we actually plot all of these data and also the intercepts and slopes. No, you know what? Never mind. It's 5:52. I'm not gonna do that right now. So let's just stop at the tidy, having things the way we have right now. So this is where you would have stopped, right? So you have you ran all that automated, and then if you just print only that object, we have f location data mod and tidy. So if we keep going here, we're not going to check Anovas because I skipped that part here for sake of time. We're not going to check residuals for the same reason. You're going to have this on the complete script later, but we're not going to do that right now. What I want to end up with and show you is I actually want to have a plot where my goal is to have a plot by location. So imagine like we're going to have facets, one facet for each location. I'm going to have potassium rate in kilograms per hectare on the X. I'm going to have potassium concentration on the Y. And I want to have the regression line that we just calculated there as well. But how do we do that if all that different pieces of information are in different nested data frames, right? So if you think about it, the data is on the data column, and the intercept and slope to be used in the plot are under the tidy column, and they're all nested. How do we get this, whatever information we need outside of this? How do we unnest this data set? Well, that's basically by using the unnest function. So if we just add the pipe here, hit enter, there's a function called unnest. And we just need to tell it what is the name of the column that we want to unnest. So in our case, at first, at least, I want to unnest the data column here. So unnest data. If we just do that, this is basically the raw data set, or not the raw, but the data set the same way that it was before we nested all the way up there on the code. So we just unnested that column. And now we're just going to create a Ggplot call that in itself, at this point, there's nothing really new or easy or magical about it. It's just how it would have been to begin with, right? So let's just add pipe and start a Ggplot call here. So Ggplot, we do not need to provide the data set name, because remember, this is what's coming in because of the pipe as the data set going into Ggplot. So let's start with the AES function. And on the X, I want to do X equals potassium rate kilograms per hectare. On the Y, I want to do K underscore PCT. I'm going to add a comma here, hit enter, and I want to say color equals F location at this top level of the Ggplot call, and group equals F location. So now I get outside of that Ggplot call at a plus, hit enter, and I want to do a geom underscore point. And I just want to say size equals 2. So outside of the AES, I just want to say size equals 2, alpha equals 0.6. So alpha is just transparency of the points. That's basically what I'm doing here. Making it 60% transparent, then add a plus, hit enter. I want to facet by location, and I want to do that by using the facet underscore wrap. And I want to say dot tilde F location. So I'm going to leave this up just for a second and run it so you see where we are right now in our plot making. So this is what we have right now. So we have K percentage on the Y, potassium rate on the X. We've got points for each one of the locations, and the locations have different colors. Okay, nice. So the next thing I want to do here is to add the regression line. And I want to do this based in our model. So this is a very interesting point to make quickly. You don't have to do this following next step, but I could just do like geom smooth method equals LM. I could run this in this case, and it would probably be very similar to actually using the model fit intercept and slope. Would be very similar. In this case, that is just a linear, like an easy linear regression model. But what if you have a nonlinear model? Or what if you have a model that has multiple explanatory variables that may not be as simple to just show this? Then you would really want to fit the model, extract the coefficients, and plot the coefficients themselves. Or maybe another way. You could also do different ways that we're not going to get into. But I'm just saying you all this to show you the alternative that is not using geom smooth, which would have been the easiest way for this case. But if you have a more complex case, it would not. So let's just add the plus, and let's use the geom AB line function. So the geom AB line works by you providing a value for intercept and a value for slope, and it makes that line for you. So we're going to come here, and here's the issue though. If the data set being used all the way up until here is basically the unnested of the data, right? So it's this part, meaning that by using this, we're not really unnesting the tidy part of it, which is where the coefficients are. So to do that, we can actually specify a different data set for each geom if we want it. In this case, we're just going to specify a different data set for the geom AB line. So we say data equals, and then we take that soy K reg all that we started with. I want to add a pipe, and I want to unnest, but the tidy column. So remember that the soy K reg all was the completely nested structure. And if we unnest just the tidy part, this is what we get. So we get columns for intercept, and if we just keep going for the K rates. So this is what I wanted to unnest for the geom AB line specifically. So this is the data set going in. Just add a comma, hit enter. Now on the AES, it has a few different aesthetics arguments. So one of them is intercept. We're going to say intercept equals to this column here, which has the same name, but it's where our intercepts are. Add a comma, hit enter. We're going to say slope equals, the slope here is the K rate kilograms per hectare. So that's what we say on slope. And then I just want to have, yeah, I guess that's basically all of it. So I can just come back here, delete that comma, and I think my parentheses are all closing right. So if we just run this, just give it a moment here, and we have our intercepts for each one of the locations that actually came from the nested tidy column on our original nested data set. So we just hit 6 p.m. The next things I wanted to show you guys here, which I had in the code, but I didn't have time to cover, was to actually include the regression equation on each one of these plots. Of course, first we would have to come back here on the nested version and do that, create a column that actually has the formula, which is not difficult, but it takes a little bit of time, maybe, I don't know, a few minutes at least, and then add that to the plot. But that's what you're going to see on the code that you receive. So I'm going to stop here because for sake of time, I just want to show you how the final product looks like. So this is the complete data set. All the way up there on the nested, I actually I extracted these values and turned this into a formula. And here on my code, I just added that formula using the geom label and unnesting this column that I called form, which is where the formula is. So this is just, this is an automated way for you to run a model, extract coefficients, create a formula, and plot it all in the same call. And the main point being that if you look at the code, this is my completed version. So maybe I shouldn't be really showing you this because it has stuff that you haven't seen yet. So I don't want to confuse you. But if you look at here, we only specified things once. We only asked to run LM once. We only asked to do tidy and do all the wrangling once. And it basically repeated those for each one of the nested data frames that in our case are different locations. So this is just how you would automate and do iteration over multiple levels of a factor and just repeat whatever task you're doing for each one of them. So this is all I had. Let's see, we have something on the chat. Oh, need to leave, great, yeah, awesome, thanks, Carlos. So this is all I had. I know that it's a very complex topic, thinking of nested data sets, that is the data set inside of another data set, and how that all works is really complicated. But it's really worthwhile to learn it because it's going to save you, it can save you a lot of time, especially if you have, you want to do something multiple times, the same thing over different data sets. So that's all I had. I'll be sharing with everyone the completed version or the completed scripts. And if you guys have any questions or comments, I'll be super happy to go over those.
Thank you very much, Dr. Bastos. Now we may open a short space for questions. If anyone has any concerns and wants to turn the mic on, you are more than welcome to ask a question or put it in the chat. So we may wait a minute for that.
And I just, while we wait here, if anyone wants to jump in, feel free. But I just want to say also, another application of doing this is something that I did in one project where we had one response variable, but we had, I don't know, almost 100 explanatory variables that we wanted to do a regression, like a correlation basically between that one response variable and each one of the 100 response variables. That's also something we can do with map. And it's very nice because you can run, all those regressions extract the p-value of them, only keep the ones that the p-value of the model is significant, so let's say less than 0.05, and then like imagine you have 100 regressions and then you filter just the significant ones, which let's say would be 10, for example, and then you focus on those 10 to make the plots and make everything nice afterwards. This is another situation that I use the map function as well that really helps with the efficiency of repetitive tasks.
Yeah, and it's nice, Leo, how you show the option of the tidyverse, now the tidy models family of libraries that is introducing more interesting options every time. So keep tabs, guys, on the tidy models, because they are offering nice features to automate and to finally pursue the reproducible science. So thank you very much, Leo, for that.
Yeah, no worries.
So if there is no any question, I will stop recording right now. And thank you very much, Leo. You are definitely the one we have on the speed dial for R and giving us always very nice workshops. Thank you very
awesome.
much.
Thanks, guys. Thanks for attending and sticking to the end. And hopefully, hopefully this can be of use for your analysis and help you to get some stuff automated as well.
Perfect. Yeah. So being that said, thank you very much, guys, for attending one more workshop with us, and we hope to see you next time.
Thanks, everybody. See ya.